let's take a look at some common applications of thermal expansion. Items will change size when we heat or cool them, and for things we build, this can put a lot of stress on them. So we may actually have to adapt the design of things so they don't destroy themselves when they attempt to creep due to the change in heat. The most common of these is the expansion joint placed in roads, bridges, and sidewalks. There are also expansion tanks for fluids to allow room for more liquid as it is heated. We can use thermal expansion in devices that can record temperature or trigger events like a shutdown when things get overheated. And new super materials like nitinol wire can use this to make artificial muscles and limbs. The expansion joints you've seen before, you probably just didn't know what they were for. And this is a testable, guaranteed testable feature because it's the most common application that you will see out there. So we take a look at this bridge, and you can see these steel fingers that slide in between each other. As the bridge gets hotter in the summertime, the section on the left and the section on the right will start to expand towards each other, and the gap in those fingers gets narrower. As the weather gets colder and the two sides of the bridge contract, they pull away from each other, and these fingers expand apart. Now remember when I said I want you to be like the scientist in movies who can look at the control gauge and go, "My God, we've got to get out of here." Or a doctor could look at his screen and suddenly you see the doctor's jaw drop and he's like, "Call the patient back in here right now." What did they see on those dials that allowed them to draw such a conclusion? So look at this expansion joint. How would you be able to tell me something about the climate where the picture was taken? How is this joint a giveaway about your climate expectations? Well, think about it. If you had a climate like Vancouver, where it just goes from chilly to warm over the year, you'd hardly expect any change in expansion. So the fingers wouldn't have to be very big. But if you were in Saskatoon that goes from -40 to +30 over the course of a year, then there's going to be a huge amount of movement on this bridge, and this expansion joint will need to be much wider to accommodate that. So here is again how a person who could look at it might go, "I've seen those things before. That's up north in Timmins," because they've had experience with working with them. Most often, the expansion joints are reserved for big engineering projects. A cheaper way of doing this is to cut the cement after it's been formed to prevent thermal cracking and frost cracking, two separate things, and we'll look at the frost one later. On a smaller scale project, they will simply form the concrete like this. It's decorative, and we'll see how it prevents cracks from forming. When cracks do form, even in steel, there's a nifty trick. You can drill a hole at the end of the crack, and it often stops the crack from going any further. So here are, looks to me like, probably they're cut. These ones were cut, not molded. And in wood, a classic thing to deal with a crack from wood stress, drill holes in front of the crack and it won't spread any further. But this is typically due to moisture change. The way the cement was cut is very ingenious. They only cut a small portion of the way in, and then when thermal stresses pull on the concrete in the cold weather, it snaps the concrete, and you basically wind up getting what they call here a Sod Contraction Joint. You get yourself a pre-made a score cut, and then the cement cracks for you. And if it's done correctly, you never see that crack. If they didn't dig deep enough or they didn't put them close enough together, the crack can travel the wrong way and you get a big split in your concrete. Here's a thermal expansion joint for plumbing. Now, it might just be a what's called a bushing, but this is in fact a thermal one. As the pipes change in size, this little gasket here can drift back and forth and correct for the pipes shrinking and expanding. Now, this here is a service cover in a street, looks like it's asphalt. And notice the shattering around it. This is due to one of two things, water freezing or thermal expansion. Let's call it thermal expansion. In any case, there's movement here that's cracked the pavement. Do you see what the workers have done? They've cut a path all the way around and filled it with caulking. And that's, well, again, the cracks have trouble traveling beyond that point. And it's worked pretty well. In your car, you have your radiator, which is full of boiling water once the car gets going. So the liquid in the radiator will expand. So you will find there seems to be a little empty white jug next to your radiator, and the fluid will expand into that, and then when you shut the car off, it'll drain back into the radiator. And this prevents that liquid from escaping. However, if you really overfilled everything, and this bucket here was full, then when the car ran, you would find the green liquid would actually fill this bucket up and start dripping onto the ground underneath the car. So this is a thermal expansion tank to prevent the radiator from pressurizing to the point it blows its lid. Now this is something I'm familiar with. I've got one in my heart. When I had my heart attack in 2013, they put a stent. And a stent is really just like a little Chinese finger trap. It's a little collapsible tube. They pop into the artery and it holds it open where the artery collapsed or got blocked. The problem with these is the stents are supposed to weave into your body and become one with you and keep that artery open. But like all metal components, they wiggle and they can get loose over the years. So sometimes these stents have traveled and it can do some pretty serious injury to you if it starts to move. So what they've been doing is making these stents out of that magic nitinol wire. And that wire expands when heated. So when they shove the cool stent into your body and then they push it out against the artery walls, very quickly your body heat makes it expand more and locks it in place until the body can heal over it and make it one piece of meat with metal inside of it. So that's a really cool new use of thermal expansion. These things are tiny. They're tinier than the spring in a pen. But the most common use you see of nitinol wire and nitinol wire are these little flappy butterflies, if you ever see. The wire curls when hot, relaxes when cool, so they just pass current and make it bend, and you can make little flappy butterflies with no motors. Perhaps the greatest failure in our lifetime of thermal problem not being corrected was the explosion of the Space Shuttle Challenger.
Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3.
The engines were then throttled up to 104% at 51.919 seconds.
Throttling up. 3 engines now at 104%.
Challenger, go at throttle up.
During the flight, telemetry data gave no indication of problems.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
You can see the solid rocket booster that they survived, but they ignited the main propellant tank.
The solid rocket boosters continued in flight and were destroyed by the range safety officer 110 seconds after launch.
The solid rocket boosters were like large barn silos, stacks of metal segments held together by O-rings and a sleeve joint along the way. These things were filled with tons of rocket fuel that once ignited cannot be put out. They were attached to the side of the spaceship in the main fuel tank. The O-ring design was to prevent when these two segments of rocket plugged together, the flame inside here from following this joint up and out. So there are several large gaskets. Now these would be rope-sized pieces. You got to remember this thing is huge. and not the kind of rubber that you and I are used to. This stuff is flame proof. You see some similar material in your wood stove if you have a wood stove with a door that's got the seal. And it turned out that these O-rings were unstable and allowing rocket fuel to go right around it. They would shrink too much in cold weather and twist out of place. And generally in Florida, you don't get that much cold weather. But it turned out in flight after flight after flight, they were seeing these little tiny jets of flame coming out of the solid rocket booster here. There's a hydrogen leak in others, but basically each segment of this solid rocket booster was occasionally letting puffs of flame out. And one day, one of those puffs of flame lasted long enough and was pointed directly at this main fuel tank and ignited it. And the whole tank just detonated.
Well, I took this stuff that I got out of your seal and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, and more seconds than that, there's no resilience in this particular material when it's at a temperature of 32 degrees. I believe that has some significance for our problem.
Dr. Richard Feynman, a very famous physicist, nailed the solution, and he literally did it at a press conference because he felt that he was getting the runaround from NASA as they were trying to cover things up, and his books are well worth reading. It turns out the day of the launch, the temperature had gone below zero a little bit, and the O-ring material pulled out. And there was the photographic evidence of this little blowtorch flame that got past the O-ring and pointed at the main tank and caused it to be destroyed.